In this next section of conservation energy and work, we're going to just take a look really quickly at the next several sheets. I'm going to tell you that I'm not going to go through these on the video. I am going to put the answers online. So if you don't remember doing this or if you haven't done it, the solutions will be on there. You might want to go back and at least review kind of what this was. And it really just kind of shows conservation of energy. So there's several pages here. Just make sure you kind of go through them and either refresh your brain or think about kind of how to do those. And if you're really lost, come see me and I will help you. Let's talk a little bit about potential energy now. So we've looked at conservation of energy. We took something that's falling and we found the conservation of energy from that. So now let's just take a look at potential energy. And we know that the equation for potential energy is equal to mgy, and the zero position of that y is very arbitrary. So you can have negative potential energy. And so let's take a look at what's going on here. In the picture that you'll see, we have Bill and we have Amber, and they've chosen a different system in terms of their coordinates. So Bill has put the rock right at 0 meters, and the lady Amber has put 0 meters on the ground. And because of that, this lady sees that the rock has 9.8 joules of energy, and the gentleman sees that it has 0 joules of energy right at this part. So it says, why is Bill's view different? Because his zero, so his 0 point is at the rock, and hers is at the ground. So that is the difference between the two. And it says, would they both get the same value for the final velocity or the final speed of the rock when it hits the ground? And the answer to this is yes. So let's go ahead and take a look and see why. So let's think about Amber first. We know that from our previous derivation that the final potential energy due to the gravity plus the final kinetic energy should be equal to the original kinetic plus the original potential. So here the original kinetic energy is 0 since it's not moving. That means that our final kinetic energy should be equal to our original potential energy minus our final potential energy. Our final kinetic energy is equal to mg times, and then we have our original height minus our final height. And if we plug our numbers in, this would be 1 times 10 times 1 minus 0. And so our final kinetic energy here is 10 joules. For Bill, who's on the other side, we have the same equation, UF plus KF. Remember, this is really UGF because it's potential energy due to gravity. That's equal to K original plus the original potential energy. We know the original kinetic energy was equal to 0. So our final kinetic energy here is equal to the original minus the final. And so this is equal to mg times the, this should be the height original minus the final height. And that's equal to 1 times 10 times 0 minus -1, since that was his definition. So here, this is also equal to 10 joules for our final kinetic energy. Because they both have 10 joules of kinetic energy, this is equal to 1/2 of 1 times v squared. And so our velocity that they both recognize that the rock is about to hit the ground at is 4.5 meters per second. So that's how we can show that they both have the same final velocity, even though they have a different orientation or a different coordinate system as it goes through. These are bar charts, so those charts that are on the previous pages, this is why they're really nice to have. Here we see that for Amber, the potential energy due to gravity is positive and the final kinetic energy is positive. And over here, Bill chose 0, so we've got still final kinetic energy is positive, but our potential energy due to gravity in the end is going to be a negative number. So this positive and this negative equal the sum of the two on this side, which is 0. And here we've got a positive blue bar, and plus 0 is equal to the positive value for this bar plus 0. So in the end, both are conserved. We've just used a different starting point for the rock. So that's how you can go through and prove that that's what's going on. This is the last part of the notes for part 2. This is a little bit closer look at potential energy. So one of the things that we're going to look at is we're going to say that we've got a Cartesian axis here. I'm going to try to get rid of, I'm going to see if I can get rid of that, that box that's kind of hanging out there. So let's get rid of that. We'll put a new thing up here. There we go. So we're going to say that going up in this direction is positive, and instead of x, we're going to use s. Because sometimes in college physics or college engineering, they'll do that. And this is positive y, and we're going to just say that s is equal to x for what we've been doing. Now, it says the analysis of motion of an object on a hill, and we're going to use calculus again. So we're going to say the sum of the forces in the x direction, okay? So remember, we said that instead of x, we're not going to use that, we're going to use s. So the sum of the forces in the s direction are equal to mass times the acceleration in that s direction. And acceleration is really just the derivative of the velocity versus time curve. So here we've got dvs over dt. So remember, s again is x. Let's go through. We're going to use our chain rule again. We're going to say sum of the forces and the s are equal to m. And now we're going to use that dvs over dt. So dvs over dt. So this is going to be equal to mass times dvs, but we don't want it in terms of dt. We want this in terms of ds, or the change in the position in the x direction. So remember, if we put that on the bottom, when we do the chain rule, we can just say that's ds over dt. And we know that ds over dt is the same thing as dx over dt, and that is velocity. So now this changes from this expression to the expression mass times the velocity in the x direction, or the s direction. That's this guy right here. So this thing became that, and now we still need to put in our dvs over ds. So let's go back, let's take a look at this diagram and see what's going on in the diagram. You'll notice that ds is the hypotenuse, okay? So that's our change of position going up the hill, and dy is going to be the height that that block is attaining. So here is our original, here is our higher height, whoops, and so this right here is going to be the change in our y position. So the sum of the forces, we said in that direction, is equal to negative, and this is the force due to gravity, times the sine of the angle. So why is that? And it's because, remember, when we draw our triangle here, we have the force due to gravity, which is mg, and then we have over on this side, we have, well, it says sine of the angle. So we're going to do Fg times the sine of the angle, and that gives us this side of the triangle. So now we've got negative Fg times the sine of the angle, which is really just negative Mg times the sine of the angle. So that's the sum of the forces, and we only want them in this direction, hence why we have the sine of the angle. So let's go ahead and put our two equations together. So we've got this one for sum of the forces, and we have this one for sum of the forces. And we're going to say negative mg sine of the angle is equal to, now we're going to do this side because that's our MA. This is just the sum of the forces, which would be on this side. So we're going to put this in. This is M times VS times DS, I'm sorry, dVS over ds. So we can go ahead and move this down a little bit. All right, now that we have our equation, let's go through and let's go ahead and I think what I'm going to do is we're going to basically just kind of switch sides here. We're going to multiply both of the sides by ds. So we're going to multiply by ds. So what we're trying to do is get rid of this ds on the bottom. And so when we do that, we're going to have negative mg times the sine of the angle times the change in the position is equal to mass times the Vs, and then notice that this ds is going to go away when we multiply both sides, so this will be dVs, so the change in the velocity in that direction. We also remember that dy here is equal to the sine of the angle times ds. And so because sine of the angle times ds is dy, this is going to be negative mg, and then instead of this, remember we said that's equal to dy, this is mg times dy, and that's equal to m times velocity in the x times the change in the velocity in that x before. So we've seen this kind of before. We know that if you have these, this is going to be 1/2 of mvo squared plus mgy original, and that's equal to 1/2 of mvf squared plus mgy final. And you're probably thinking, oh my goodness, how did you go from this to this? So we've skipped a bunch of steps. If you remember in the first video, we went through and we integrated both of those. So here's that mvy dvy over dy. Here's the mg dy. It's essentially the same thing. And if you integrate both of those sides, then you end up with that conservation equation. So there it is again. Mg dy is equal to m vs dvs, and we do our integration on both sides, and then you'll end up with this equation. So now that we have that equation, you do remember that that is our kinetic energy original plus our potential energy due to gravity original, and that's equal to our final kinetic energy plus our original potential, our final potential energy due to gravity. It really doesn't matter which side things are on. You could have the final here and the potential here, but in the end, you just have to make sure that your equation is correct. So remember, we did integration to get to this, so I'm just going to draw that and just put integrate our differential equation. So once we've done that, we're all set. So we've been able to go through this twice. We did it once with something that's falling, and the second time we did it with something that is going up a hill. And there's that hill that we've climbed. And that is the end of the second section of the notes.